Hi, today we will discuss how to design a web application for streaming music. We will cover not only the front-end part but also touch on specific aspects such as streaming protocols and different audio formats. Let's begin. We start with a brief introduction, during which we discuss references, address clarifying questions from our hypothetical interviewer, and gather requirements. Next, we turn our attention to the architecture encompassing the primary layers of the application, like UI, data models, API, and other elements. Following that, we take a closer look at the process of streaming music. We discuss how we plan to implement this in the browser, including the formats, technologies, and approaches we intend to use. Subsequently, we explore a general topic common to most major web applications, such as offline mode, performance, and accessibility. Additionally, we delve into specific details of our application. And finally, we conclude by consolidating all requirements to ensure nothing has been overlooked. First and foremost, we need to find references for our application. Designing an app without a clear vision of what we are working on can be challenging. While we can and must ask clarifying questions to the interviewer, it's essential to be familiar with the context. In our case, possible references include Spotify, Apple Music, YouTube Music, and SoundCloud. These applications encompass a wide range of features such as audio playback, playlist management, and the ability to download music for offline usage. Since it's impossible to cover all features during the interview, we must ask with the interviewer about the specific areas on which we should focus on. So let's move to the questions. First, we need to determine which features we should support. The answer is that we should show recommendations on the main page, allow users to search by track, artist, or albums, and provide additional artist information when users click on an artist name. Next, we need to understand whether we should support an offline mode, and if so, how it should be used. The answer is affirmative. We should allow users to download music for offline listening. Many music apps like Apple Music and YouTube Music offer standalone experience, where users can launch them separately as native applications. Do we need something like this? Having a native application would be useful. However, it's important to note that designing a native app isn't the responsibility of a front-end developers usually. So we need to consider how to achieve it with limited resources. Lastly, inquire with the interviewer about any additional features that applications should have. Additionally, we should support seamless playback, ensuring that playback continues uninterrupted regardless of user actions on the page or when switching between devices. Now we are ready to collect the requirements. Since the interviewer has provided a clear picture of their expectations, it should be relatively straightforward for us. In different situations, we should refer to the features of similar apps and ask more clarifying questions. So let's start with functional requirements. Users can listen to music. Playback should not be interrupted by any actions on the page. Users can search by track name, artist, or album. User can click on the artist name or album to access more information. We should build and display personal recommendations for users, such as popular songs or tracks from their favorite genres. We should synchronize the state between different devices. If a user starts listening to a song on their desktop and switches to a mobile phone, we should remember the last played song. Non-functional requirements. The application should be accessible to people with different disabilities. It should perform efficiently. It should be internationalized. It should have an offline mode, allowing users to download tracks for offline listening, and it should work well on various types of devices. Now is a perfect moment to check all requirements with the interviewer before beginning designing. It's better to ask questions now rather than spend time developing the wrong features. Let's look on the high-level architecture. This is an initial overview and we will add more details later. However, let's review what we have so far. We're using the classic model view controller pattern, or MVC. I prefer this pattern because it's well suited for describing a typical web application. Separating components into layers provides a reliable and clean architecture, allowing changes in one layer without affecting other parts of the application. The architecture consists of three main components: view, controller, and model. Our schema is more complex, so let's delve into the details. The view, or UI, is the visual layer responsible for displaying UI elements on the page. In our case, it includes four main components: main screen, artist screen, search screen, and player. The main screen is the initial page which users see when they open the app, where we present recommendations to the user. The artist screen offers detailed information about artists, including descriptions and list of songs and albums. Search is a separate page in our case, as it might include multiple entities such as songs and artists, requiring ample space to display results effectively. And player is responsible for playing music. The controller serves as the core of our application, responsible for connecting the view and model. The view doesn't fetch data directly from the model or server. It does it through the controller. The same applies to writing data. The view doesn't directly update the model. Instead, the controller handles view events. The model consists of two parts: the client store and the responses cache. It is crucial to distinguish between these two types of stores. The client store is for storing client-only data, including input values, sorting parameters, or, for example, last scroll position. Everything not received from the server and not requiring synchronization with it. On the other hand, the responses cache stores server responses and typically contains immutable data. We have separated API model into a distinct layer, only responsible for handling network requests related to the server. All interactions with the server should occur in this model. In other words, the controller works with the API model as if it's unaware of the server's existence. With the front-end side complete, let's now turn our attention to the backend. We have two servers, app server and web server. The web server is responsible for delivering assets like JavaScript, CSS, and HTML files, and the app server primarily managing data-related tasks. For example, when users request a song search, the app server handles the request and returns the results. Let's look on the user interface. Normally, you shouldn't sketch the UI during the interview, but it can be helpful to have a mental picture. Keeping the overall UI design in mind can help us to create a more cohesive application. Here's the main screen with recommendations, which includes other things like recent releases or most popular songs. The next is a search screen, displays the results of a search, including songs, artists, and albums. An artist page provides additional information. Notably, each screen includes a player, as one of the requirements is to ensure seamless playback. The next question is how we should render the application. There are two primary options: client-side rendering and server-side rendering. Each has its suitability in specific cases. Client-side rendering is easier to develop and maintain. It provides smooth transitions between pages without additional load time. However, it has bad search engine optimizations, first contentful paint, and time to interactive metrics. From the other side, Server-side rendering provides good search engine optimizations and good time to interactive and first contentful paint. However, it also has slower transitions between pages, as we need to make requests to the server for each page, and it's more challenging in development and maintenance. Client-side rendering and server-side rendering are base solutions that can be enhanced. For instance, in client-side rendering, we can implement preloading assets and displaying loaders until the application is fully rendered. In the case of server-side rendering, we can implement iteration to render a static page on the server and quickly deliver it to the users. But this results in a non-interactive page for some time. We can improve iteration by using partial iteration and progressive iteration, topics that require more in-depth exploration. Before selecting an approach, we must consider our priorities. Since we're designing a web app, fast initial loading is essential, but not as critical as for a landing page. Good search engine optimizations is necessary primarily for promotional pages, but not for the app. We expect our application will be highly interactive with numerous on-screen elements that must function smoothly. And most importantly, we must ensure continuous playback, which rules out any form of server-side rendering. Based on these priorities, we can extract the main requirements: fast switching between pages and continuous playback without page reloading. Client-side rendering fulfills both of these requirements. However, it comes with significant downsides. If we load the entire bundle and start executing JavaScript on the client side, it may take too much time, especially on low-performance mobile devices, leading to what's known as the blank page problem. In some cases, user may look on a blank page for more than 10 seconds, which is unacceptable. We must find ways to improve this. We can utilize client-side rendering along with preloading. By showing users a skeleton preloader, we can eliminate the impression of a frozen page, which might lead users to leave. Additionally, implementing aggressive code splitting by using modern bundlers like Webpack or Rollup allows us to split the JavaScript bundle into smaller chunks. In our case, this could result in 3 chunks: one for main page, one for artist page, and one another for search page. We can go even further by breaking these chunks into smaller parts, more specific components, and lazily loading pop-ups and other assets that are not immediately necessary. The key idea here is to combine client-side rendering with efficient code splitting and preloading, so the bundle size scales according to the application size, preventing unnecessary loading. The next topic is data model. Our data model comprises 3 primary entities: song, album, and artist. Each song has one or more authors and optionally belongs to an album. Each album consists of one or more songs and has one or more authors. Both albums and songs should be associated with one or more genres. Genre is represented as an enum with predefined string values like rock, pop, classic music, etc. Each entity has a URL field such as song URL or artist URL, which is necessary for sharing. For instance, if a user likes a song, they may want to share it with friends, requiring a shareable link. We have discussed the data model, but now we need to address how data will be transmitted between the web application and the server. There are 3 main options: REST API, RPC approaches, with gRPC developed by Google being the most popular, and GraphQL API. REST API is the most flexible and straightforward approach, suitable for various API structures. It interacts well with browser caching and offers a rich set of tools. Finding developers experienced with REST API is generally not a problem. However, its flexibility can lead to a lack of standardizations, as REST is essentially a set of rules rather than framework. Each developer or team decides which rules to follow, making it challenging for new team members to work with APIs that may deviate from expected norms. Additional checks are often required to validate responses from the server. RPC approaches differ significantly from REST. Instead of describing entities, RPC focuses on methods. For example, consider a method called deleteItem. In REST, you would use the entity name and the delete method, whereas in RPC, it resembles a plain function in, for example, JavaScript. The idea behind RPC is to abstract the technical details from the end users. Users simply request the deletion of an item and the method handles the rest. RPC offers several advantages. High performance, strong security, code generation allows to automate endpoint creation, contracts to ensure data consistency between the backend and the frontend sides. However, RPC is not natively supported by browsers and can be more complex, often used for cross-server interactions. And then there is a GraphQL. GraphQL is a powerful query language that allows fetching only the required fields, making it a ideal choice for situations where entities are tightly coupled. For example, like in our case. GraphQL supports features like code generation, static analysis, and offers a good developer experience. When considering trade-offs, it's challenging to find some particular weaknesses in GraphQL. It does add complexity to development, but any other tools do the same, and its suitability depends on the specific use case. Unlike REST API, GraphQL is not a general solution, and it's not suitable in many cases, like, for example, streaming. Before we go further, it would be useful to clearly understand what tightly coupled data means. In our scenario, we are dealing with three main entities: song, artist, and album, all of which are tightly interconnected. There is a high chance that at the same point in the app, we will need to simultaneously access several fields from the songs entity and at the same time fields from the artist entity. Without GraphQL, we would be required to make two separate requests for these two entities and then merge them on the client side. However, with GraphQL, we can simply make a single request. Moreover, in the case of the REST API, we might potentially have to request all fields from both entities, which is typically not needed. As mentioned earlier, GraphQL permits the fetching of only the required fields. Before choosing a protocol, let's consider how our app will interact with the server. First, we need to stream audio files. Authorization support is crucial. Our entities are tightly coupled. For example, fetching artists with all their albums and songs is a typical request. Not all fields are necessary on every screen. For instance, the main screen may require only the song name and cover. By clicking on it, could reveal more detailed information. Based on these considerations, we can identify two primary requirements: fetch only the data that is needed and support streaming and authorization. GraphQL effectively addresses the first requirement. However, we also require support for streaming and authorization. Therefore, the best approach is to use two protocols together: GraphQL for data and REST API for all other interactions. Certainly, this approach is more complex to develop and more expensive. However, it offers scalability and becomes more valuable as the application grows. The next topic is Backend for Frontend, or BFF. It's an additional layer positioned between the frontend and the backend. The idea behind a BFF is to create a dedicated backend for each user experiences, such as mobile or desktop, instead of having a single general-purpose API backend. Alternatively, you may opt to have one BFF server serving all clients. Now, let's explore situations where you might need a BFF. When your app is used across various devices, each with distinct requirements and capabilities. For instance, mobile devices usually have lower performance, but they have access to features like the camera and QR code scanning. when there is additional logic or intensive computations that can be moved from the client side to the server. Certainly, supporting an additional server requires additional resources. So if you decide to use it, be prepared for increased expenses. Moreover, your team should have some knowledge of backend development. In our scenario, the frontend team would be responsible for both the web app and the BFF. In our case, we need to manage more than one client, at least desktop and mobile clients, making the addition of a BFF a sensible choice. Additionally, since we have recently chosen to incorporate GraphQL, the BFF is a suitable place for its implementation. Let's consider the apps architecture after adding the BFF layer. We have placed it between the client and the backend, which means every request passes through the BFF. In the BFF, we have implemented both a GraphQL API and the REST API. On the backend side, we still have only REST API. Moreover, if we need features that the backend doesn't currently support, say custom data filtering, we can implement them in the BFF. The backend typically should be more robust and generic since it handles many clients. It might not always be feasible to add specialized code for each client, as it can lead to unmanageable complexity. The BFF, on the other hand, is a flexible layer designed to serve specific clients or client types. One of the roles of the BFF is to handle resource-intensive computations instead of doing it on the client side. We won't go deeper into the API specifics since we have opted for GraphQL for data handling, which abstracts away much of the complexity. If you're unfamiliar with GraphQL, it's a query language for APIs and a runtime for fulfilling those queries with your existing data. GraphQL empowers clients to request precisely what they need and nothing more. The primary point of our interest is to implementation of the search functionality. As you might remember, we need to implement searchers across multiple entities simultaneously: artists, songs, and albums. We might request users to specify the category before searching, and we should retain this filter in search settings. By default, the search should work across all entities. On the backend, we determine the best matched results and send them to the client. We initially display, let's say, 5 songs, 5 artists, and 5 albums. The exact count depends on the screen size and can be larger on desktops. If this isn't sufficient, users can click on a More Results button for a specific entity. This leads to at least 4 distinct endpoints: one for mixed search results, one for songs, one for artists, and one for albums. The next significant topic is streaming, a core feature of our application. Let's go into the details. First and foremost, let's differentiate between streaming and progressive downloading. Progressive downloading is the method used by the HTML5 audio element by default. It involves downloading audio in chunks and allows user to start playing content immediately after the first chunk is downloaded. Progressive downloading has 2 key distinctions from real streaming. Meta content is stored in the user's device browser's cache. Users cannot jump to a specific audio segment. They must wait for all previous segments to download. With streaming, the browser doesn't store the audio in memory. Instead, the audio is streamed directly to the user's device. A helpful analogy is that when you click the pause button with progressive downloading, playback is paused on the client side, while the audio continues to download in the background. With streaming, when you click pause, both playback and downloading from the server are paused simultaneously. Let's discuss the pros and cons of each approach. Progressive downloading provides instant audio playback. The track starts as soon as the first chunk is downloaded. Users' traffic savings. Files are downloaded once and can be cached for later use. Support for offline operations. Files are stored on the user's device. and it's easy to implement. HTML5 audio elements inherently support progressive downloading. However, it lacks support for fast seeking, meaning users can jump to specific audio segments, potentially increasing their data usage. Progressive downloading also raises security concerns, as files must be stored on the user's device. As a result, several advantages come with trade-offs. Progressive loading is used for short tracks, where fast-seeking features and security are crucial. From the other side, streaming offers fast-seeking, efficient bandwidth utilization, and enhanced security. However, it's not useful when users don't have an internet connection, as it doesn't store files on the device. It also requires more complex development and maintenance. Streaming is ideal for longer tracks that require fast-seeking features and security. In our case, where we might have short songs or long podcasts and aim to protect audio files from unauthorized copying and distribution, streaming is a preferable choice. Streaming isn't natively supported by browsers, so you need to use Media Source Extension or MSE to enable it. Media Source Extensions extends the capabilities of video and audio elements, enabling dynamic changes to a media stream without requiring plugins. This technology supports features like adaptive media streaming, live streaming, video splicing, and video editing. MSE provides native streaming support for the HTML5 audio element without the need for additional browser extensions. Previously, apps had to rely on browser extensions like Flash or Silverlight to enable streaming. Even if you don't plan to stream extended tracks, implementing MSE can be beneficial as it offers greater control over content delivery, including support for custom protocols. Furthermore, if your audio content requires digital rights management or DRM for protection content, MSE allows you to handle encrypted audio streams, ensuring secure distribution and playback. The one challenge with MSE is browser support. As a fallback option, you can utilize the native HTML5 audio element for progressive downloading. Now let's consider the streaming protocols. While HTTP is the default option, it natively supports progressive downloading. RTMP or Real-Time Messaging Protocol is a communication protocol used for streaming audio, video, and data over the internet. Originally developed by Macromedia for use between Flash Player and the Flash Communication Server. HTTP Live Streaming, or HLS, is an adaptive bitrate streaming protocol developed by Apple. Dynamic adaptive streaming over HTTP, or DASH, also known as MPEG-DASH, is an adaptive bitrate streaming technique that enables high-quality streaming of meta content over the internet delivered from HTTP web servers. Similar to Apple's HLS solution, MPEG-DASH works by breaking the content into a sequence of small segments which are served over HTTP. HTTP supports only progressive downloading, not streaming, but it's straightforward to implement. RTMP supports streaming, but it requires additional extensions to be installed. Both HLS and Dash are modern solutions. HLS has better browser support due to its age, while MPEG-Dash is format independent. In other words, we are not limited in choosing an audio format with Dash, whereas HLS supports only AAC, MP3, AC3, and EC3 formats. So if we opt for HLS, we are limited by these formats. So what is suitable for our case? We can't use HTTP as the primary approach since it doesn't support streaming. RTMP lacks native browser support and requiring users to install additional extensions to use our app would be inconvenient. HLS is natively supported through Apple software, but Dash and HLS are well supported via MSE. Let's look at the streaming protocols used by popular streaming services. YouTube Music supports both HLS and Dash. Apple Music supports only HLS. Spotify employs its own proprietary protocol. For our app, we will use Dash because it's modern, supports streaming, and it is codec agnostic. The next topic is audio formats. Since we have chosen Dash, we have the freedom to select the most suitable audio format for our needs. The oldest format, MP3, is widely supported, and MP3 files have relatively small sizes. However, there are better alternatives available today in terms of quality and size. One such alternative is AAC, or Advanced Audio Codec. It's an audio codec standard for digital audio compression designed to succeed the MP3 format, offering higher sound quality at the same bitrate. While MP3 and AAC were designed for playing audio files, the next two formats, Opus and Agvorbis, were especially designed for streaming audio content. Opus provides good quality and a wide range of bitrates, while Agvorbis offers better quality than MP3 at similar bitrates. It is widely used by streaming services and is open sourced, which may be advantageous depending on our company's goal. Let's see what real applications use. YouTube Music supports AAC and Opus. Apple Music supports AAC and Apple Lossless Audio Codec, or ALAC, which is open source and royalty-free. Spotify uses AAC and Agvorbis. For our service, we prefer to use AAC and Agvorbis. Agvorbis is designed for streaming purposes and is open source, which is generally favorable. As not all browsers and devices support streaming, we also have AAC as a fallback. Other streaming services typically allow users to change the bitrate to suit their needs. Additionally, it is possible to adjust the bitrate dynamically through streaming via MSE, Dash, or HLS, depending on the user's network conditions. In some cases, there may be browser compatibility issues. Some browsers do not support MSE with certain audio formats. It means that we need to support different audio formats based on the browser. That's why it's important to support at least two formats to provide broader device compatibility. In our case, AC plays the role of the format supported by major devices and browsers. The next topic is encrypted meta extensions. Encrypted meta extensions provide API that allow browsers to interact with Content Protection System, or CPS, which includes Content Decryption Module, or CDM. Meta content is encrypted, so users cannot access it outside the application. This is necessary to prevent illegal distribution. This requires the use of special servers that provide access to this content. Such servers are called DRM servers. The EME is the provider between the encrypted meta content and the DRM server. Now we have more details about our system. Let's see how CDM and DRM interact with the other components. First, the API requests the audio file metadata, including the audio URL. After receiving the metadata, the controller passes it to the player's component. Next, the player sends a request to the AME, which calls the CDM that built into the browser. The CDM requests a license key from the DRM server. The DRM server generates a license key and sends it to the client. The client passes the key to the CDM, which then decrypts the meta content. And finally, the user gains access to the content. Additionally to using MSE, we can take it a step further and use the modern web audio API. However, not all browsers support it. We may implement a graceful degradation technique. Depending on the browser, we will approach one or multiple of the following solutions: HTML5 native audio element, MSE, and Web Audio API. The HTML5 audio element offers very basic audio playback. The Web Audio API is more complex but provides additional features such as mixing, processing, filtering, and crossfading. The HTML5 audio element has better support from browsers. MSC falls in the middle. It has relatively good browser support, but lacks some features found in the Web Audio API. In our case, we will start with the HTML5 audio element as a fallback for all the browsers. Depending on the browser, we will upgrade the audio player, progressing to the next step. In other words, for users with older browsers, we will provide the minimum required features, allowing them to still use our application. For users with modern browsers, we will offer all possible features. Let's look on the comparison. We begin from the left side. The native audio element is a very basic solution. It's easy to develop and has good browser support. However, it has limited features. Media Source Extensions has many more features, including preloading and streaming via HLS and Dash. However, browser support is less extensive and it requires more resources for development and maintenance. And for Web Audio API, it provides numerous audio-related features like mixing, processing, filtering, but browser support is worse and it demands a certain level of expertise to work with effectively. As we discussed earlier, we plan to implement all these approaches, but we'll utilize them depending on the client's browser. The next feature is an offline mode. Offline mode is crucial for streaming music applications. Users want to access their music catalog when they don't have an internet connection. Imagine a scenario where a user downloads music in advance to listen it during a flight. So, what features should offline mode support? We should display the current network status and inform the user that they are offline, while also prompting them to go to the list of downloaded files. Users can browse downloaded music, and of course, they can play it. But how can we make our application work when users have no internet connection? If the browser can't reach a remote server, it simply returns a not found error, right? Yes, unless we find a way to intercept it. Service workers can help us here. Let's look at what a service worker is. Service workers are built in the browser. Service workers act as a proxy between the web application and the backend. Service workers can listen to incoming requests, pass some of them to the network, and store a copy of the response for future usage via the Cache Storage API. The Cache Storage API is for storing assets such as HTML, CSS, and JavaScript files. It serves as a browser's cache for storing data fetch responses. By utilizing the Cache Storage API, service workers can reduce network utilization even if we don't need offline mode. In simple terms, service workers allow us to cache assets, store them, and use them offline. When a user has no connection, we can simply retrieve the page from the cache. Let's see how a service worker works together with the Cache Storage API when a user has an internet connection. First, the application requests assets, HTML, CSS, and CSS files. The request is intercepted by the service worker. The worker checks the cache storage. If assets are cached, they are retrieved from the cache and returned to the web application. If the assets are not cached, they are fetched from the web server. The web server sends the assets to the web application. The service worker stores the assets in this cache storage. Next time they are needed, they are retrieved from the cache without a request to the web server. And the service worker sends the assets to the web application, and finally, web application uses them to render the page. However, without content, assets are not very useful. What is the use of blank pages if users can't do anything with them? Storing assets is not enough. We should also store media files. Of course, we can't store all the music on the user's device, but we can offer them the option to store their favorite tracks or any other tracks. What we can use for storing metadata? We have two options. Local storage. The only advantage of this is that it's easy to develop. It has limited capacity, typically 5 or 10 megabytes depending on the browser. It doesn't support binary files and has a slow synchronous API. Another option is IndexedDB. It offers a relatively larger capacity. For example, in Chrome, it can use up to 80% of the available space and allocate a maximum of 75% of the space for each origin. It natively supports binary files, has a fast asynchronous API, and is a feature-rich client-side database. However, the wealth of features leads to a very complex and convoluted API, which can discourage many developers. In our case, we have no choice. Local storage is not suitable because it has really small capacity for storing media files. Therefore, we opt for IndexedDB. You may wonder, why not use the cache storage API, which we use for storing assets, for storing media files as well? The cache storage API provides a limited set of options and does not give us enough control over the downloading process. It doesn't allow us to easily pause and resume download, track the progress of downloads, or properly respond to HTTP range requests. HTTP range requests ask the server to send only a portion of an HTTP message back to the client. Range requests are useful for clients like media players that supports random access data tools that know they need only part of a large file, and download managers that allow users to pause and resume downloads. For instance, if we're downloading several files, some of them may be large, and we can pause some of them and continue with other to prioritize loading and perform other tasks. Therefore, we need more control over downloading and storing media files. Before we move to the file downloading, we should know how to decrypt media files. As you remember, we're using DRM to do that in normal situation. However, without internet connection, it becomes impossible. Persistence license may help us. Persistence license can be stored in a local license store on a device, and playback clients may reuse the license repeatedly until it's removed or becomes expired. Persistent licenses are needed when we don't have access to the license server due to no internet connection or for another reasons. The disadvantage of persistent license is that you cannot revoke them before they expire. The license should be valid for a limited time, approximately 1 week, after which it must be refetched when the user accesses the internet. We are using a persistent license to decrypt files and allow users to listen to audio content. Now that we have all needed elements, let's see how downloading music should work. Assume that the user has already downloaded the music and we have put it into the IndexedDB. Now let's look at the offline scenario. The web application is trying to retrieve the data, but the user has no internet connection. Since we can't download the assets from the server, we need to retrieve them from the cache storage to render the page. The application goes offline, shows the network status, and prompts the user to go to the download directory. We assume that the audio files has been preloaded by they are encrypted. The user uses the preloaded persistence license to access the files. The next topic is a native application. It would be nice if our users could use the application separately from the browser. It is very convenient and gives us more control. We assume that we don't have a dedicated team to develop a desktop app. So the same team will develop the web version and the native version. The native application should be relatively easy to develop for the frontend team. In other words, it must use web technologies. We have two possible options here, Electron or alternatives, and progressive web application. When talking about Electron, we don't forget that Electron is just one tool that utilizes web technologies to provide a native experience. It has its pros and cons, so feel free to use any Electron alternative that is more suitable in your case. Electron is a framework that allows developers to build applications compatible with macOS, Windows, and Linux using web technologies like JS, HTML, and CSS. Electron is cross-platform. Electron allows you to build desktop applications that can run on Windows, macOS, and Linux without major modifications. Access to native APIs. Electron apps can access native system features and APIs, making it suitable for building future-rich desktop applications. It has a large development community. Electron has a large and active community, which means you can find plenty of resources, plugins, and support. It's independent. Electron works separately from the browser. It's an independent instance of Chromium. However, it has bigger size. Electron apps tend to be larger in size compared to PWAs, as they include a bundled version of Chromium along with your app code. Since Electron apps run a separate instance of Chromium, they can consume more system resources, leading to potentially higher memory usage. A progressive web applications is a type of application software delivered through the web, built using common web technologies, including HTML, CSS, and JavaScript. It is intended to work on any platform with a standard compliant browser, including desktop and mobile devices. It is cross-platform. PWAs are accessible through web browsers, making them cross-platform and compatible with various devices. It has smaller size. PWAs are generally smaller in size compared to Electron apps since they do not require a bundled runtime like Chromium. It has better search engine optimizations. PWAs can be indexed by search engines and discovered like regular websites, potentially increasing your app's visibility. However, it has limited access to native APIs. PWAs are still limited in terms of accessing certain native APIs and system features compared to Electron apps, and also it's browser dependent. PWAs shares a Chromium process with a browser. It means that users can't close the browser if they want to keep the application workable. It also means that the PWAs share resources with the browser. So what is better? Based on the description of both approaches, we can conclude that PWA is a good for cases when we don't need all the features of the native API, and at the same time, the speed and simplicity of development are important. Developing a PWA is much easier than building an Electron app, and Electron and alternatives are a good choice when we're developing feature-rich applications that need to access native APIs and system resources. Real YouTube Music uses a PWA. You can identify it by opening it in a browser and looking for the PWA icon. In Chrome, it's located on the right side of the address bar. I don't know what Apple uses for Apple Music. Spotify uses Chromium Embedded Framework, which is one of the alternatives to Electron. For our service, we will use a PWA. Initially, this is more suitable. We don't know whether our application will be successful or not, so we can't allocate time and resources to build a complex native application. A PWA provides us with the possibility to launch a mobile app and desktop app relatively easily with minimal resources. Now let's talk about the streaming optimizations. What if a user wants to play a favorite songs many times? How can we optimize this scenario? Just as we store saved music, we can also store frequently played music. The only difference is that this data needs occasional cleaning. This means we can turn to our old friend IndexedDB once again. If we discover that a user is replaying a song rather than streaming it, we can download it and save it into IndexedDB. Let's see how it works. When a user begins to reply a song, we first need to check if it's already saved locally in IndexedDB, assuming that IndexedDB does not contain such a file. The web application requests the file from the CDN. The audio files are then transferred to the client. Once all the chunks are downloaded, we can group them together and store them in IndexedDB. The audio file name should not be used as a key. In fact, the ID should be used. When the user wishes to replay this song, it will be retrieved from IndexedDB without a network request. Let's discuss synchronization. We anticipate that our application can be used on a variety of devices. A user might start listening to an album or song at home and then continue listening from a mobile phone while outside. We need to store the following playback information: current song, the point from which playback should continue, and playback context. The playback context includes the list to which the current audio file belongs. It could be an album, a list of favorite or recommended songs, or something else. We need the context to determine which audio file should be played next or previous. The playback context may also contain other useful information. Memorizing the point from which playback should continue may not be very convenient for short tracks, but it is useful for long DJ sets and podcasts. We may implement it for audio longer than 10 minutes. So let's see how it works. When a user starts playing an audio file, either manually or automatically, we send all the necessary data to the application server. Later, when the user switches devices or browsers, we retrieve this information to continue playback. We know that the current audio files belong to a specific album or list, and we know the track's position. From the album ID, we can determine which track should be played next or previous. Consider how we can implement the feature to remember the last playback point. Imagine a user listening to a long audio track, like a podcast. They wouldn't want to start from the beginning every time. We can't use local storage for saving this position since users may switch devices. The only options here is to store it on the server side. If we do that, how often should we update the state? We can't do it too frequently as it would create a heavy load on our servers. Yet, we can't do it too infrequently either. Possibly, we can send one request when a track is stopped for any reason. Think about both scenarios or explore alternative solutions. The next topic is adapting the application for mobile devices. Mobile devices differ from desktop. They have smaller screens and generally less powerful processors and memory. We must consider these specifics. We shouldn't download high-resolution images on devices with small screens. We can use the src set and the picture HTML elements to control which image to load. Mobile devices, including cell phones, usually have touch screens. While this offers certain possibilities, it also presents limitations. Hover and focus events are not possible on touch screens, so we must find alternative ways to interact with the app. All interactive elements should be large enough to ensure the touch area is bigger than the visual size of the element, and text content should also be large enough to be readable on small screens. On small screens, we can't afford to display wide banners, large decorative elements, etc. The user experience should be centered on the main content. We can use CSS meta queries to create different versions of the user interface. And finally, we should avoid aggressive preloading as mobile devices typically have slower internet connections and limited data traffic. Performance is a broad topic and we can't cover it all. I prefer to categorize it into 5 areas: network, images, audio, UI, and JavaScript and CSS. I've grouped JavaScript and CSS together because they are both related to the code. From the network side, we can use data compression, gzip, and Brotli. Brotli is a relatively new compression algorithm developed by Google. It employs a modern compression algorithm optimized for the web and generally achieves better compression ratios than gzip. Protly is particularly effective on text-based files formats like HTML, CSS, and JavaScript. However, it's not widely supported as gzip, which means that some older web browsers may not be able to decompress Protly files. gzip, on the other hand, is an older and more established compression algorithm that has been used on the web for many years. It is supported by virtually all modern browsers, ensuring that your compressed files will be readable by the majority of users. gzip is also a good choice for compressing binary files, such as images and videos, as it can achieve good compression ratios on these file types. The other recommendations are use the latest version of protocols, such as HTTP 2.0 or higher, implement caching assets, which we did via Cache Storage API, request the minimum required fields via the GraphQL API, preload critical data, and defer loading non-critical assets such as pop-ups and IDS scripts. For images, we will employ lazy loading, meaning we download an image only when it's needed. We will also use modern media formats like WebP for images and WebM for videos. Although we haven't discussed video in details, if included, we should prefer using the WebM format. WebM is an alternative for WebP but for videos. We should load the appropriate image for each screen using the src set attribute and picture HTML element. For audio files, we will use modern audio codecs such as AAC and Ogg Vorbis. Additionally, we are using the modern Dash streaming protocol, which allows us to stream audio files instead of downloading them, saving user storage space. For elements that we can significantly speed up, we can at least make them appear faster. Instead of standard spinner, we can use skeletons with a shimmer effect. These skeletons simulate a real UI, helping user better understand how the final page will look. We should also provide smooth transitions, such as fade-ins, slide-ins, or animations between screens and other interactive elements on the page. We should utilize lightweight icon fonts or SVGs for icons and buttons and avoid loading redundant fonts. We might even go further and limit font variations and symbols downloading only what's necessary. In JavaScript, we should avoid JavaScript animation when possible. Additionally, we should steer clear of heavy computations on the client side, opting to move them to a web worker or to the server side. Recognizing that operations with DOM elements can be resource intensive, we should strive to reuse DOM elements instead of creating and removing them whenever it's possible. Finally, we should split the bundle into chunks. As we discussed earlier, when using a single-page application, it's crucial to divide the application into chunks and load them only when needed. Regarding CSS, we should prefer CSS animations. However, it's essential to be aware that CSS animations also have performance costs. The safest animations in terms of performance are opacity and transform animations. We should follow naming conventions like BAM, unless we're using other approaches such as CSS modules or styled components. Naming conventions not only help maintain code consistency but also improve performance, as only the first-level selectors are highly efficient. First-level selectors consist of a single selector. The next topic is accessibility. While it can vary depending on the specific app, we can focus on some general recommendations. For all non-decorative images, we should use meaningful alt attributes. Use appropriate role attributes. The role attribute describes the function of an element for programs that can make use of it, such as screen readers. Use area label or area labeled by for interactive elements without labels. When an element doesn't have accessible name, especially in cases like buttons with only icons, the area label attribute can be used to provide a meaningful label. Pay attention to color contrast to ensure readability and accessibility. This can be checked using tools like Lighthouse, which is built into Chrome. Ensure that all interactive elements can be navigated and operated using a keyboard. Include transcript for audio content whenever possible, and make sure that errors are clearly communicated both visually and through screen readers. The next topic is internationalization, which involves preparing application for translating on different languages and translating text content. Preparing application for translating on different languages includes things like attempting to predict the user's locale using a combination of the accept language HTTP header and IP address. However, users should also be allowed to change it if they wish. Remember that one country may have multiple languages and users may use VPNs. Consider differences in word length. Carefully review the user interface, especially interactive elements. Pseudo-localization may be helpful here. Pseudo-localization is a technique used for testing localization. It involves using a pseudo-language instead of a real language. It keeps string readable but highlights problematic areas common to real languages. It helps quickly identify places without translation and can involve adding some characters to the pseudo-translation to identify inflexible UI elements. Avoid using string concatenation, as words may appear in different places in different languages. Do not put text in images because it's not scalable, and use logical properties instead of directions. These steps can significantly improve the accessibility and user experience of your application for a global audience. Now let's focus on the next question. How do we translate the text? In order to translate the text effectively, we need to decide on the format for saving translations and the method we will use for translation. Format options include JSON, ICU message format, getText, and other formats. Translation methods includes TMS or Translation Management System, Internal Translation Team, External Translation Team, and other options. Before selecting a format, it's essential to choose an approach to translation. Not all formats are compatible with all methods. I have prepared a table that outlines approaches suitable for different project sizes. On the left side are approaches that work well for small projects, while the right side presents scalable approaches more suitable for large projects. Translation agencies and freelancers. Medium to high cost, depending on the project size. Quality varies, but it's usually good enough. Low vendor lock, as we can change agency easily since we manage translations on our servers, and it's suitable for small projects usually. Translation software or API. Medium budget. Quality depends on the underlying translation model. Low vendor lock, as we can easily change software. Suitable for small to medium projects. Localization service. Bigger budget than simple translation. Low to medium vendor lock. Ideal for medium to large applications when launching in different markets. And simple text translation isn't sufficient. Internal translation team. Good quality but can be costly. It may be free if part of a larger company with an existing team. It's suitable when planning long-term app development. TMS or Translation Management System. A system designed for managing localization and translations. Suitable for projects with a big budget and substantial scale. High vendor lock, so choose carefully. Each approach has its advantages and limitations, making it crucial to align your choice with your project's specific needs, budget, and long-term goals. Next, we must determine the format in which we will store translations. Not all services work with all formats, so this decision is critical. First one is JSON. JSON is a human-readable format. It's easy to work and very flexible. Well, flexible JSON lacks specific standards for translation management. You will need to create your own structure for handling translation within JSON files. This format may not offer as many features as dedicated translation libraries, potentially limiting your ability to handle pluralization, context, or dynamic text formatting. GetText format. In contrast to JSON, GetText was especially designed for translations. GetText is the oldest format among these three and is well established for managing translations in software development. GetText supports essential features like pluralization and context, making it suitable for a wide range of translation needs. However, GetText may have a steeper learning curve if you're not already familiar with it. GetText files are not human-readable as JSON files, which make translation management slightly more challenging. And the last one, ICU, or International Components for Unicode Format. ICU is an open-source, cross-platform set of libraries providing Unicode and globalization support for software applications. It supports numerous features including date, time formatting, numbers, currency formatting. ICU is the most powerful among these three formats, but is also the most challenging to learn and work with. It is most suitable for projects with complex translation requirements, but may be overkill for smaller projects. While many services support JSON, it's essential to check whether the services you plan to use support GetText or ICU if you opt for these formats. In our case, since we don't anticipate highly complex translations, JSON serves as the most universal format. It is especially suitable if we have an internal translation team. Alternatively, we can utilize translation or localization software depending on our expansion plans for other markets. Translation agencies and freelancers are preferable when developing a website or a small web application without scalability ambitions. In such cases, they can be more convenient than building a system to interact with various devices. Translation management systems may be an overhead for our application since we don't have an extensive amount of text to translate. And that's the conclusion. Let's review all the requirements once more to ensure we have covered every aspect. Let's examine the functional requirements. Music listening. We have addressed audio files delivery and implemented a graceful degradation approach for music playback. We have discussed the search functionality, both its general operation and its application for specific entities. Users see personalized recommendations on the home screen when open the app. Synchronization between devices. We have introduced a system for synchronizing the current track and context across different devices or browsers. Now let's consider the non-functional requirements. Our app is designed with accessibility in mind, following best practices, to ensure it's usable for people with various disabilities. We have taken various approaches to guarantee the high performance of our application. Our development includes an offline mode, allowing users to use the app even without an internet connection. We have taken steps to ensure our application functions seamlessly on various types of devices, and internationalization. We have prepared the application for translation into different languages. That's all for today. I will include all the relevant links below. If you found this video useful, please don't forget to click the like button and subscribe to the channel. Stay tuned for more upcoming videos. Thank you for watching and see you next time. Bye.